Yesterday we did a demonstration where we sent a wave pulse down through a slinky and it encountered a boundary. The first boundary was between the slinky and a hand. And we found that when that wave hit the boundary between the slinky and the hand, two things happened. There was always, no matter what, there was always some transmission and some reflection. In other words, some of the wave kept going. You saw the hand moving as a result of the energy being transferred from the slinky to the hand. Some of the energy kept going, some of the wave was transmitted, but you also saw that some of it was reflected. We went out into the atrium and did a little demonstration as well where we had the slinky wave reflecting off of the slinky air boundary. Again, you saw that some of the wave transmitted and some of the wave was reflected. We saw that when the media or the materials were very different, like slinky and hand or slinky and air, then most of the wave was reflected. There would still be some transmitted, but most would be reflected. Similarly, we would see that if the two media were very similar in nature, then most of the wave would be transmitted and only a little bit would be reflected. So you're always going to get some of both. How much reflection, how much transmission takes place simply depends upon how close the two media are together in nature. If they're very similar in nature, most of it will be transmitted, only a little bit will be reflected. If they're very different in nature, then most will be reflected and only a little bit will be transmitted. Now let's spend a little bit more time talking specifically about the part of the wave that is reflected. We know that the wave can go from a medium that's less dense to a medium that's more dense, or it can go the other way around. When the wave goes from a medium that is more dense to less dense, in other words, when it's not connected to the other end, then we're going to find that the wave is reflected right side up. That's the demonstration that we did in the atrium, right? You remember? We sent the wave pulse down through the slinky. Slinky is more dense. It reflected off of the slinky air boundary. Air is less dense. When it reflected off of that boundary, when it was going from more dense to less dense, or when it wasn't connected to something, then we found that the wave was reflected right side up, or upright. So I'm going to say that it's reflected upright when the wave goes from more dense medium to less dense medium. And the way that it usually manifests itself is if the mediums are not connected, right? There's no attachment, not attached. Conversely, we saw in our little demonstration of the classroom, when we had one person holding on to the end of it, and the slinky was attached to something, the wave was going from something that was less dense to more dense, then we found that the wave is reflected upside down. I don't expect you to necessarily memorize the words, visualize the demonstration that we did, right? Okay, we see that, was it Jack that was our volunteer yesterday, I think? Yeah? We saw that if we saw that demonstration yesterday, we saw the wave when it reflected off of Jack's hand, reflecting upside down. Remember that. Remember that picture in your mind. And then you can the words just kind of flow after that, right? So we're going to say that the wave is reflected inverted or upside down when we're going from a less dense medium to a more dense medium. And the way that that normally manifests itself is when the medium that it's coming from, the medium it's going to are attached. The slinky was attached to Jack's hand yesterday. The slinky was not attached to the air as it was in the atrium when we did our little demonstration. So more dense to less dense, it's going to be reflected upright, right side up. Less dense to more dense, it's going to be reflected upside down. Now we weren't able to do this part of the demonstration yesterday because it's not physically as easy to do as the part that we did. But if we were, we would find that if we sent a wave down towards a boundary and we examined the reflected part of that wave as it reflected off at an angle as opposed to straight on like we did in the demonstration yesterday, we would find that it would reflect off still right side up, upside down, depending upon whether it's going to more dense or less dense, but it would reflect off at the same angle as it struck it at. So in other words, if we draw that little dotted line that we call a normal line that is perpendicular to the boundary, and then label an angle right here from that normal line to our wave that is striking the boundary, that's reflecting off of the boundary, and then draw another angle, we'll call it theta 2, that represents the angle that it's reflecting off of the boundary, either right side up or upside down, depending upon less dense, more dense, then we would find that theta 1 would always equal theta 2. In other words, we call it the angle of incidence is equal to the angle of reflection. At some level, we intuitively know that, right? If you're playing pool and you want to hit the white ball around the 7 ball, let's say, sometimes you bank it off the side. And when you bank it off the side, you know intuitively that you have to hit it at this angle because it's going to bounce off at that same angle. Or if you're throwing a ball against a wall and you want it to go over there, you know what angle you have to throw it against the wall at because intuitively you know it's going to bounce off at the same angle. Waves behave the same way. When they strike a boundary at an angle, they reflect off at the same angle. Either right side up or upside down, depending upon whether it's going from more dense to less dense or less dense to more dense. What about the part of the wave that is transmitted? Well, we don't worry about right side up or upside down here in the transmitted portion of the wave, or the wave that keeps going, because it's always going to be transmitted right side up. But there are some things that do change and some things that remain the same. And that's what we want to focus on here. The part of the wave that's transmitted will always have its speed changing. The speed will either increase or decrease. When light goes from air into glass, the speed of light decreases quite dramatically. When sound goes from water into air, the speed change, it decreases quite dramatically. If sound goes from air into steel, let's say, the speed will increase quite dramatically. The part of the wave that keeps going into a new medium will have either an increase or a decrease in the speed of the wave. And as a result of that, we will see an increase in or decrease in the wavelength of the wave. If the speed increases, then the wavelength will increase. If the speed decreases, then the wavelength will decrease. Always. There's another one that sometimes changes, but we'll look at that in just a moment. Okay, we'll focus right now on the ones that always change. What always stays the same when a wave goes from one medium to the other? Or anytime, once a wave has been produced, this property will always stay the same. Yeah, the frequency. The frequency never changes. Once a wave has been made, there it is. That's what you got. Forever and ever and ever. Now I said there's something that changes sometimes, but not always. I want to draw a picture to help illustrate what it is that sometimes changes and why it sometimes changes. Let's say we've got a boundary between a paved parking lot. Okay, this is our pavement down here. And for whatever reason, right beside this paved parking lot, there's a swamp up here. Let's say we've got a bunch of soldiers marching in this paved parking lot for whatever reason. I'm not sure why. Maybe it's, I don't know, maybe it's a parade or something. These soldiers are right here, 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 here. There's 6 of them. 6 of them in this parking lot. We're looking at them from above. So we draw a line that joins these soldiers together, and we visualize that as our wave front. So if we were flying in a helicopter above the ocean, we would see the crest of a wave. Okay, if we're flying in a helicopter above this parking lot, we would see this line that joins these soldiers together. It would be analogous to the crest of a wave. Now, this is where they are at this moment in time. 2 seconds later, this soldier is going to be up here. Now, soldiers march in stride, right? So 2 seconds later, this soldier is going to be right here, right here, right here, right here. But this soldier has slowed down. How come? Why is this soldier not traveling as fast as the other guys now? Because he or she is in the swamp. This is half a meter of water, and you can't walk as fast in a half a meter of water as you can in paved parking lot. So he or she has slowed down. Now, we're up above this in a helicopter. We draw this imaginary line that joins together all the soldiers, and now it looks like this. 2 seconds later, soldiers are up like this. These 3 soldiers all marching at the same speed, but now we got a couple more soldiers in the water, or in the swamp here. We draw the line now that joins them all together, and it looks like this. Another one, 2 seconds later. Now only 1 soldier is not in the water. All the rest of them are in the swamp. They've all slowed down except for the one. And we find that it looks like this. You can see here that the speed of these soldiers, the speed of this imaginary wave has changed, has decreased because we've gone into the swamp. We can see as well that the wavelength has changed. This was the distance between crests, the wavelength. Now this is the distance between crests, or the wavelength. So the speed has decreased, so is the wavelength. But in addition to the speed and the wavelength decreasing, what else has changed? What else has changed besides how fast these soldiers or this wave is moving and the direction that the wave is moving? How about the direction? The direction that it's moving, right? The direction of the wave front was this way. Now the direction of the wave front is this way. So we're going to say that theta, or the direction, sometimes changes. The direction will change if we strike the boundary at an angle. If we strike it straight on, the direction is going to stay the same. V and lambda will change. But if we strike it at an angle, V and lambda will still change. But as a result of that, theta will also change. Doesn't matter what happens, F is going to stay the same.